Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, today we will discuss about magnifying power of telescope. Students, today we will discuss about the magnifying power of telescope and we will discuss how many types of telescopes are there. Basically, telescopes are of three types. One is astronomical telescope, the other one is terrestrial telescope, and the third one is Galilean telescope. In our portion, we'll be discussing only about the astronomical telescope and we'll see how we can find the magnifying power of this astronomical telescope. So before we start, let us understand the basic concept of astronomical telescope. It is just like a compound microscope where we have two convex lens used. In compound microscope, we are using two convex lens. Here also we are using two convex lens. But thing is that there the objective was smaller and eyepiece was bigger. Here the objective lens is bigger and the eyepiece lens is smaller. This is so because we want to see the distant object. In telescope we see distant objects. In microscope we see nearer distance, nearer objects and smaller in size. So therefore the objective has to be bigger. The focal length of objective has to be greater. So let us start with the magnifying power of telescope. Magnifying power of telescope. As I told you, I'll just explain a bit. Telescope. In astronomical telescope, we use two convex lens. Here, the final image that is formed is inverted. Here, we are using three convex lens and the image formed here is erect. Here, one convex lens and one concave lens is used. Our focus will be only on astronomical telescope. The basic difference between the astronomical telescope and terrestrial telescope is that for astronomical telescope we see very distant object like the stars or the different planets. But in case of terrestrial telescope we see the distant object only on the surface of the earth. For example, if you want to see the distant hill or any distant place only situated on the surface of the earth, then we use terrestrial telescope. So let us now try to find the magnifying power of astronomical telescope. Now, magnifying power. the definition of magnifying power is that it is the angle subtended by the final image at the eye to the angle subtended by the object at the lens. So, in case of the magnifying power of telescope, so this is the formula. This objective and the eye both will mean the same thing here, because compared to the distance of the object, the distance between the lenses are very small. So we can say that angle subtended by the distant object at the eye is same as the angle subtended by the object at the objective lens. So let us first understand with the ray diagram how we'll find the magnifying power of telescope. So now I will take objective, this is the objective, this is a convex lens, and this one is the axis of this convex lens. This is center, optical center, and the ray has to be, because the object is at infinity, so the ray are coming parallel to this objective lens. And the ray which is coming passing through the optical center will go undeviated, something like that. Now this ray will go straight without making any deviation, because this is optical center, so ray must go undeviated. The other ray must be parallel to this, so I can draw another ray over here, but I will not draw that because that will complicate the situation. First let me draw with a single ray, and then I can lightly put the other one also. So here this is the this is the image of the distant object which is from here. I will call this as A and B. This is the image of the object, and this image is real and that is inverted. This is inverted because the object is at infinity, so obviously the image is formed at the focus or focal plane of the lens. So this is the focal plane on which if the rays are parallel, then if they are parallel to the optical axis, this axis, principal axis, then it will be at focus. But if they are parallel but not parallel to this principal axis, they will be forming their images at the focal plane. So this is the focal plane where the image is formed. So obviously this distance from the center of the lens to the point where the image is formed, this distance is known as the focal length of objective, because the image is formed at a distance. Obviously it has to be at a distance of focal length, because that is the property. Now this image that is formed due to the first lens must act as the object for the second lens, that is the eyepiece. So this object AB, this image AB of the objective lens will act as object for the eyepiece. So I'll keep one eyepiece over here. This is the extended part of this lens. So I will draw like that because I cannot draw like this. Anyway, so this is the ray, and if this will be at the focus of this eyepiece, this is the eyepiece, this object, if it is placed at the focus of this eyepiece, that means we have to adjust the, by rack and pinion arrangement, we have to adjust the position of this lens, the eyepiece lens. We adjust the position of the eyepiece lens such that the image formed by the objective falls on the focus of this objective, this eyepiece lens. Therefore, if this is placed at its focus, then this distance is FE. This is the focal length of the eyepiece. So this is the object distance for this lens. So therefore I write FE equals to UE, because this is the object distance and that is equal to the focal length of the eyepiece. Now I am just doing one particular case, that when the object is placed at infinity, the image is formed at the focal plane of the objective lens, and the image formed is at a focal length from the eyepiece. Okay, so therefore this special case that the final image, the image formed by one objective is at a focal length of the eyepiece. So in that case, if the object is placed at a focal length of any convex lens, its image is formed at infinity. But here that will be formed at infinity, so this ray will go up to infinity. So I will write like this, that if I consider one ray, such rays, like this. If you see from here, if they exactly focus, then this will run up to infinity. If these rays are extended in the backward direction, this will meet at infinity. So the final image will be formed at infinity. If the focal, this image is formed within the focus of the eyepiece, then we'll have a virtual image here, inverted, and at this point somewhere here. So in that case we will have another options, but in this case we have this one. And let me tell one thing, that this image I have drawn bigger, this lens looks smaller, so the angle is not properly drawn. But anyway, these rays has to be parallel because the object is at focus, and the angle this ray makes at this eyepiece, because our eye is also here, this angle is suppose beta, this angle is alpha, this is the angle that the distant object makes at the objective lens, this alpha, this becomes alpha, this angle is beta, this is the image, whatever is the final image formed, that is beta, because this is at the focal length of this lens. Now according to definition of magnifying power, it has to be the angle beta divided by the angle alpha, because that is the magnifying power definition. The final image, whatever angle it is obtained at the eyepiece, and 2 divided by the angle that the object projects at the objective lens. So therefore beta by alpha. And what is this beta? This beta is tan beta, I can write, and in this triangle, or in this triangle, because this is, I will consider very close to each other, the diagram is not properly drawn, so this distance, this triangle, so this tan beta is this side by this side, so it is if this point is E, this point is O, then BE divided by AB. So it is tan of beta divided by tan of alpha. Here it is BE divided by BA. This is for tan beta, divided by the tan of alpha. You can see from here the tan alpha is this P by B, AB upon this. So this alpha, this beta will find the magnifying power as beta by alpha. That beta can be written as tan beta divided by tan of alpha. In this triangle, I'll draw the triangle for you. In this triangle, this triangle, because when they are parallel, I'll not consider that this distance is this ray and this ray are different, both of them, because this lens is very small. If I will draw another diagram for you to justify the statement, but for the time being, just remember that this angle is beta. So this image, whatever angle projects at this point, is same as this part of this forming at this point, that is beta. So therefore this is in this triangle, this is AB divided by B, this triangle, this distance by this distance, but then this distance is similar to this distance. I will say that this object or the image, final image, if you take infinity final as in final image, then if this goes backward, then whatever the final image, wherever it is formed, that will project the same angle beta. So I'll write, and whatever is the size of that image, obviously it will be bigger than this BA. Suppose this is BA, now it will be more bigger than that, but the angle will be same. What I want to say is that this one, this is now AB, and if I extend in the backward direction, suppose that the final image is formed here, but they will project the same angle here, that is beta. Whether this final image forming whatever angle it is here, the same angle is projected by this. So therefore we are not concerned with this line or this line, we are concerned with this angle. So I can take the angle from this triangle or this triangle. So instead of taking this triangle, I will take this triangle, because I am interested in beta, not in the sides. So therefore AB upon this is point E, so I will write AB upon BE. So this is 90, so tan of beta in this right angle triangle is this side, AB upon BE. Similarly, from this triangle ABO, tan alpha is AB upon BO. Now now I can cancel AB, and this will be BO upon BE. What is BO? BO is FO and BE is FE in this situation. So this is FO upon FE. So magnifying power is phi. In case of image, this is the case of magnifying power if image is formed at infinity. If the image is formed at infinity, then this is the case. In general, we will also write the general expression for the magnifying power. So let us do that also. In that case, I will not draw the lens, just give you the picture. Suppose this lens is placed here, convex lens. This is our AB, and this is the lens, the eyepiece lens, and that is extended in the backward direction, because another ray will go from here and that will be going, one will go straight, and suppose the image that is formed is somewhere here. This is A dash B dash. I can complete the lens. This angle is alpha, this angle is alpha, the alternate angle, this angle is beta, this angle here I, this is the eyepiece. So, and this distance is focal length of objective, but if the focus of this lens, eyepiece lens, is here, then this is the focus of eyepiece lens, then this is the focal length, but then this is not used, this one is used, that is objective distance, this one. So in normal situation, so this is the angle subtended by the distant object, this is the angle subtended at the eyepiece by the final image. Now we will divide that two angles, one the beta which is finally drawn and the initial angle alpha. So in that case, the tangent of beta divided by tangent of alpha, that is the magnifying power, and that is equal to beta by alpha, because beta and alpha are very, very small. In small angles, you can replace beta by tan beta, sin beta. So in this case, I have replaced beta by tan beta to use this triangle to find to express this angle in terms of sides. So this tan beta in this diagram of this triangle A, B, and this point, suppose this point is E, because this is the optical center of the eyepiece, this is objective lens, this is the optical center of objective lens, so let us say this is O. So one point is the optical center of objective, the other one is the optical center of eyepiece. So with respect to those 2 points, if I consider this triangle ABE, then if you draw this triangle ABE here, this is A, this is B, this is E, this angle is beta, so tan beta will be the perpendicular upon the base. So this AB, this will be AB divided by the side BE. Similarly, tan alpha can be obtained from this triangle, because the object is at infinity, so you cannot draw alpha or find alpha in this side of the lens. So we have to switch over to the other side because of the symmetry, that this angle is this angle. So I will use this triangle ABO to find alpha. So ABO is something like this, AB, and somewhere O is here, and like that. This angle is alpha. So I will write tan alpha from this triangle, it is AB divided BO. Now AB will get cancelled. I have BO divided BE. What is BO? If you look at the diagram properly, you see that this BO, B and O, this AB is the image of the objective lens when the object was placed at infinity. So this position of the image and the distance of this position of the image from the objective lens is called the image of this objective lens, and this is obviously formed at focus because the object was infinity. So the final image is always formed at focus. This is the focal length. So this image distance is focal length, so I'll write FO. So in place of BO, I'll write this is the focal length, so I'll write FO divided by BE. This one I have not taken as this image I have not kept at the focus of the eyepiece, I have kept in between the focus and the optical center. So the image has to be formed away from this, in the same side but virtual, and it will be magnified. So therefore this image distance, I have this object distance for this BE is UE, because the image formed by the objective acts as object for the eyepiece. So FO upon UE, this is the magnifying formula for a general case, but then we have to write UE instead of UE. You have to write expression in the form of V or FO, FE. In that form you have to write, because questions are given in the form of, they are not giving you in the form of UE. You will be asked to find VE, FE and FO are always given to you in the question. So you have to write this expression of UE instead of in form of VE. So to do that, again we have to go for the length equation. The length equation is 1 by V minus 1 by U is 1 by F. This is the length equation. Now I will substitute the values of here. I am going to apply this equation for which lens? There are two lenses, objective and eyepiece. Though you have to keep in mind that I am going to apply this for the eyepiece, not for the objective, because I am interested in UE, not UO. So therefore this is equation is applied at the eyepiece lens. So therefore this will be 1 upon VE minus 1 upon UE, and this is 1 upon FE. Using sign conventions, so convex lens, the focal length is always positive, and depending on the position of UE and VE, they are taken positive or negative. In this situation, the image and the object, both the image and the object, this is the final image, this is VE. The image and the object both are the left side of the propagation of the ray of light, so they are negative. So I'll write 1 upon minus VE minus 1 upon minus UE, and therefore that is equal to f of 1 upon FE. Focal length is positive in case of the convex lens. I want to get rid of this 1 upon UE, this becomes plus, so 1 upon UE equals to 1 upon FE plus 1 upon VE. This is negative, to the other side it becomes positive. So from here I will find UE, and that comes out to be, this is just like product upon sum, so it is FEV upon FE plus BE. This expression we have to use in place of UE. So therefore the magnifying power of telescope can be written as that FO divided by UE can be replaced as FO divided by FEV divided upon FE plus VE. This is just what we got. Now just put this here, product by sum. Now this is the general expression, and this formula has to be remembered. Now there are two conditions. One, where to get the images. In case of telescope, if nothing is mentioned, then image is supposed to be formed at infinity, and in case of a compound microscope, the image has to be formed at dDV if nothing is mentioned. So we will consider both the cases, that image is formed at infinity. This is the first case. If the image has to be formed at infinity, the final image by the eyepiece lens, then the object has to be kept in its focus. So therefore the object distance UE has to be equal to FE. So for this UE, the object distance has to be FE, that is the focal length of the eyepiece. So if I substitute this, and the final VE becomes infinity, so VE becomes infinity. So I will just replace that. I can use this, or I can use directly the formula I have got. Magnifying power is FO by UE formula. From this I will get FO by UE, which is equal to FE. So this is the formula when the image is formed at infinity. I'll just use the previous value. So this is the formula, and in case of with sign convention, proper sign convention, we will come to the conclusion that if I use sign convention, then this will become negative, because focal length is positive and this is negative, so finally this will become negative. Similarly, I can put negative over here, I can put negative over here, I can put negative over here. In any way, because both are positive, this has to be negative from the beginning, this has to be negative. Now, so using that, This also has to be negative. Put the negative with sign convention, or you put sign negative whenever the numerical is there. Now what is the length of the telescope? The length of the telescope is the distance between this lens and this lens. That is distance between the objective lens and the eyepiece lens. What we have seen in the diagram is that the objective is placed here, the eyepiece is placed here, the distance is this distance, that is OE. So basically the length of the telescope when the image is formed at infinity is the distance between the objective and eyepiece. So therefore this is L, length between O and E. That is equal to, you can see from the diagram that this is this length up to this length plus this length, because the object has to be placed at infinity. So the better diagram will show here that when the object is formed at the image is formed at final image is formed at infinity, this distance UE has to be FE. So therefore already it was FO, so it was FO plus FE. This is the length. Obviously this has to be positive because we are interested in the length. We will not consider the sign convention. So this is the length of the telescope. Next situation is that in the second case, when the image is formed at DDV, that means the VE final image from the eyepiece VE is D. Then in that case, what is the magnifying power? The magnifying power formula I have to use the same formula that I have used here, that is FO FE plus VE divided by FE VE. This formula I have to use. So here in place of VE I will replace this VE by D and rewrite the equation. So the magnifying power is FO, this is FE plus D divided by FE into D. So again I will take this inside and separate. So this is first term will become FO FE by FED plus FO D by FED with sign convention. No problem with that. With sign convention, this is the final value I am getting here with sign convention. So now this FE will cancel out, this D will cancel out, and I am getting minus of FE FO upon D plus FO upon FE. From here, if I take minus FO common, then I will get 1 by D plus 1 by FE. Or if I take common, that's all. Or I will take the LCM minus FO, then FE plus D divided by FE into D. This can be written as minus FO, I take common again FE outside, then inside I have FE plus D divided by D. This I will write as minus FO by FE and 1 plus Fe by d. So this is the final expression for the magnifying power of the telescope when the image is formed at ddb, the distance of distinct vision. So in this case we'll see that this is the final expression, and in short, to remember this formula we have a shortcut, that is magnifying power of a system is the magnifying power of individual lenses. M1, M2, you just multiply and so on. So here we have to use two lenses. So one is the objective, the other one is the eyepiece. So we'll multiply the magnifying power of magnification of both the lenses. That will also give you the result. So in this case, the magnifying power of this one, these two lenses are respectively F0 by Fe. This is the one magnification, and the other one is 1 plus Fe by Fe over d here. So we'll multiply those two and we'll get the magnifying power of the system. So in this situation, that is if you find the length of the telescope, then when the length of the telescope and the image is formed at ddb is FO plus UE. This is the expression. Again, you can write UE in terms of the V, as we have seen that UE is nothing but V Fe upon V plus Fe. That I am not going to write, but that you can write that. So that is FO plus UE, which is FO plus UE is VE Fe divided by V plus Fe. So this formula you can use. In the questions you will be given everything, then you can put that value here to get the value of the length of the telescope. So this is how you find the magnifying power of telescope. Okay, thank you.